Hi guys, here is MIH. Today's video is a bit unusual in that it features no experiments but focuses on a single reaction, decarboxylation. What's more unique is that it's going to be in a style similar to proper chemistry review papers, and in fact I probably could compile the contents of this video into a manuscript and send it to journals. A decent academic review usually centers on a reaction, discussing the known reaction conditions, mechanism, notable applications, and further development directions, etc. And this video has all of these features. It consists of a brief but compact overview of the reaction's history, as well as around 40 examples of decarboxylation reactions, each with detailed reaction conditions and procedure, while also diving deep into the mechanisms, trends, and side reactions, and finally looking forward into future development of the reaction. The main distinction of this video from boring chemistry review papers is that it includes amateur chemistry as a formalized branch of chemistry within the scope of discussion, at a position equal to synthetic chemistry, chemical industry, and biochemistry. This is, of course, an approach that no academic journals would take, but honestly, I think people should pay more serious attention to the field of amateur chemistry. It has its own unique rules and challenges, and can be just as fun and fruitful as the usual standard chemistry, with the obvious prerequisite of sufficient theoretical knowledge, adequate lab skills, and proper protection. But anyways, that's quite a digress, and now let's actually embark on this journey. Chapter 1. History, Past, Present. Decarboxylation is one of the oldest organic reactions, if not the oldest. Hundreds of years ago, long before modern organic chemistry theory emerges, people made acetone through the pyrolysis of acetate salts, and even developed it into a large-scale industrial production route. In 1760, French chemist Louis Cadet heated a mixture of arsenic trioxide and potassium acetate to produce a mysterious liquid with an absolutely horrible smell. Nobody had any idea of what is happening, but now we know that the content of this Cadet's fuming liquid is dicacodyl and cacodyl oxide, regarded as the first two organometallic compounds ever made, which marked the beginning of a new and later prolific branch of chemistry, organometallic chemistry. However, as time progresses, new organic reactions are discovered very rapidly, and decarboxylation began to lose its significance in both industrial and lab settings, such as the acetone route being supplanted by the cumene process in the 20th century. However, as new disciplines like biochemistry and amateur chemistry develop, the old reaction was picked up like a treasure. Countless biological processes essential to life forms proceed through decarboxylation, like the citric acid cycle converting acetyl-CoA to energy and synthesis of the neurotransmitter serotonin from amino acid 5-hydroxytryptophan, and new enzyme-catalyzed decarboxylation routes to synthesize exotic chemicals are developed rapidly. Meanwhile, decarboxylation proved to be a surprisingly versatile tool for home chemists on synthesizing useful reagents that are otherwise difficult to obtain, like the conversion from nicotinic acid to pyridine and salicylic acid to phenol you may be already familiar of. In the next 5 chapters, we will go over significant examples of decarboxylation reactions. Each reaction is supplemented with great detail. Properties of the reactant and product, reference price from reagent companies, reaction mechanism, typical reaction conditions and yield, whether this is generally the best method, either internet video or scientific literature references, and finally, which of the 4 fields this reaction relates with. Chapter 2. Reactions with aromatic substrates. This part features most prominent examples of decarboxylation being used in amateur chemistry, as well as a few lesser-known reactions also useful synthetically. I'm sure most of you know this, heating the food preservative sodium benzoate with alkali to form benzene. Generally, the yield of these solid-state reactions depends heavily on proper heat transfer, and I've seen a 90% reported yield with small batches. Analogously, toluene may be prepared from toluic acid in areas where toluene is not easily available, and all 3 toluic acid isomers may be used equivalently. Aniline is industrially made from hydrogenation of nitrobenzene, but it can be produced from the common food supplement p-aminobenzoic acid in decently high yields, which I also demonstrated in one of my past videos about the oldest synthetic dyes. Notably, the carbon dioxide byproduct protects the aniline from oxidation by air, so exceptionally pure aniline can be obtained easily without the need of redistillation. Pyridine is usually obtained by amateur chemists through this route, apart from buying it directly, but the special catalyst copper chromite must be used to guarantee high yields. Similar to the route to aniline, the route from salicylic acid to phenol has no industrial significance, but is a way to produce crude phenol. Pyrogallo is still industrially produced the way it was initially discovered by the legendary Swedish chemist Carl Wilhelm Scheele, which is decarboxylating gallic acid by heating. Furan is industrially made by the decarbonylation of furfural obtained by biomass, but a convenient laboratory preparation utilizes 2-fluoric acid, also available from furfural by oxidation or the Cannizzaro disproportionation. Chapter 3. Reaction with non-aromatic substrates. This part is probably familiar to amateur as well as most professional chemists, because beside amateur syntheses, it also features some robust and elegant organic reactions still in practice today. Viewers in China should know this reaction very well, as it is the textbook method to prepare methane gas by heating sodium acetate and soda lime. Of course, this reaction is only limited to a laboratory setting. Nitromethane can be obtained, although in low yields, by the reaction between sodium chloroacetate and nitrite to form nitroacetate, and a subsequent decarboxylation. The well-known and time-honored route from calcium acetate to acetone, of course, won't be forgotten here, but I strongly recommend against it due to its low yield and horrible purity of product. However, another example of ketonic decarboxylation, the synthesis of cyclopentanone from adipic acid, gives a much higher yield due to its intramolecular nature, and is even used in industry nowadays. The reaction is also famous as the first step in the amateur cubane synthesis completed by many YouTubers. This oxalic acid decarboxylation route represents one of the only few amateur routes to formic acid, as the acidification of formates usually results in low yields due to the acid thermal dehydration. And here comes the big stuff. Until now, the first reaction we've encountered that is related to all four fields. The legendary Robinson-Tropinone synthesis, bringing the versatile but expensive drug atropine to large-scale use worldwide, is a prototypical example of biomimetic reaction, as the biosynthesis of atropine proceeds through a very similar route and intermediate. The only video demonstration I found was Cameolus' video on Abno, which uses glutaraldehyde instead of succinaldehyde, and hence his product contains one more carbon than tropinone. Next up are two reactions usually placed side by side in university organic chemistry courses, the acetoacetic ester synthesis and malonic ester synthesis. Their twin relation is seen easily, as the reaction conditions and mechanism are almost identical, and only the product differs. This is a lesser-known reaction that was formerly the industrial synthesis route of food preservative sorbic acid, and I would obviously recommend purchasing the product instead of making it. Chapter 4. Reactions with redox. Until now, all reactions we've encountered involve no external oxidizing or reducing agents, but now we're going to step into the more complicated field of organic redox. Interestingly, the substrate for the Robinson-Tropinone synthesis, acetone dicarboxylic acid, is itself prepared by decarboxylation. However, some sources report that the reaction expels carbon monoxide instead of dioxide, making it not a decarboxylation and not even a redox reaction anymore. But I think that carbon monoxide can't be produced as it will be easily oxidized by the oleum. And here we meet another pair of twins, Hunsaker and Cauchy reactions. They both utilize a transition metal-based oxidant to convert carboxylic acid to an alkyl halide, and some sources even call Cauchy's conditions a modification to Hunsaker's reaction. The decarboxylation reaction most frequently used in organic synthesis is the Barton decarboxylation, which proceeds through a unique radical mechanism that grants it exceptional functional group tolerance and thus its wide application. Coincidentally, it also appeared in the cubane synthesis, making two decarboxylations appear in a single synthetic route. Last but not least, we have a rather unusual reaction, the Kolbe electrolysis, being one of the only few organic reactions involving electricity. Its low yield and limited substrate scope results in its limited application in lab and industry, but now new techniques like waveform-controlled electrolysis emerges to change the game. Chapter 5. Rarely used and emerging decarboxylation reactions. This is a section for a reaction that works on very specific substrates, find niche uses, or haven't been fully developed and understood. Sodium chloro-difluoroacetate serves as an in situ source of the active intermediate difluorocarbene, which then participate in cyclopropanations, bond in certain reactions, or Witted-like reactions to produce difluorinated products useful as candidate drug molecules or synthetic intermediates. Decarboxylative cross-coupling is a very new field that developed rapidly in the recent years. Following the discovery of various transition metal catalyzed cross-coupling reactions, using carboxylic acids as alkyl precursors had become ever more popular due to the complexity of synthesizing and handling coupling partners such as boronic esters, Suzuki reactions, and trialkylstananes, Still reactions. Another key advantage of decarboxylative cross-coupling is that the carboxylic acid can act as either the nucleophilic or electrophilic coupling partner, depending on catalyst, reaction condition, or the other partner, making the coupling reaction extremely versatile and adaptable to various substrates. The hammock reaction is a less-known reaction, featuring the decarboxylation of pyridine 2-carboxylic acids to carbenes and its subsequent addition to carbonyl compounds, forming 2 pyridyl carbonyls. The substrate is strictly limited to pyridine and quinoline alpha carboxylic acids, making the reaction less useful. The Crabtree decarboxylation is unique in that it directly converts esters to decarboxylated products without needing to hydrolyze the ester first. However, its harsh temperature conditions limits its use. Chapter 6. Biochemical Reactions. Despite its name, this section isn't all about reactions happening in biological conditions. Many reactions useful in synthetic chemistry and amateur chemistry are inspired by biochemical processes. The decarboxylation of proline to pyrrolidine is a perfect example. Although the decarboxylation of proline isn't common in organisms, the reaction can still be carried out abiotically by heating an acetylphenone, which serves as both the solvent and the catalyst. Of course, you would imagine other amino acids to decarboxylate similarly, and that is the case for 6 structurally similar amino acids known as the aromatic amino acids. Perhaps surprisingly, their decarboxylation is catalyzed by a single enzyme known as aromatic L-amino acid decarboxylase, or alternatively, DOPA decarboxylase. All 6 aromatic amines produced by this way are active messengers or neurotransmitters in the body, with serotonin and dopamine being perhaps most well known. The enzyme's catalytic mechanism can also be explained easily with standard organic chemistry, involving the formation of sheaf bases connected to a pyridine ring of paradoxal coenzyme. In fact, this active site structure and catalytic mechanism is shared in this enzyme catalyzing our next reaction, namely ornithine decarboxylase. Here, lysine and ornithine are decarboxylated to produce cadaverine and putrescine respectively. Interestingly, this reaction can also be done under abiotic conditions by heating the amino acid hydrochloride salts with sodium bicarbonate, but the industrial production does not rely on this route. Normally, the biochemical decarboxylation only occurs to a very small extent in living animals, but after the organism dies, the enzyme begins generating these diamines, which, I think you can tell from their names, smell just like a dead body. That's why I recommend against replicating this reaction even in a lab setting. Just as a final side note, the citric acid cycle essential to most life forms also involves multiple steps that release carbon dioxide, but their mechanism is much more complicated and involves redox coenzymes like nicotinamide adenine dinucleotide or NAD, so I'm not going into the reactions in detail in this video. Chapter 7. Common Reaction Mechanisms. After detailing many examples in the previous chapters, the next 2 chapters will be devoted on summarizing the trends, patterns, and guiding principles behind the reactions. First up is the carbanion mechanism, which bears similarity to the electrophilic unimolecular elimination mechanism, or SE1. It is the most classic decarboxylation mechanism and features the formation of a carbanion. The stability of the carbanion determines the reaction's ease, so carboxylic acids with strong electron withdrawing groups decarboxylate easily. The 6-member ring mechanism is also very classic, but only applies for beta-ketonic acids. Its key step is an intramolecular rearrangement through a cyclic transition state, making the reaction's energy barrier very low and thus easy to happen. The radical mechanism is the less common one. It is initiated either by heat or by radical initiators, and proceeds through chain propagation and termination steps. It is the basis of 2 named reactions we've previously covered, the Hunsdiecker and Barton decarboxylation. The concerted proton transfer mechanism wasn't something that the academic community fully agreed on yet. The key step is proton transfer between substrate and solvent by hydrogen bonding, which explains why certain carboxylic acids like salicylic acid are prone to decarboxylation, as well as why the decarboxylation of barium adipate in the absence of water produces no cyclopentanone but only cyclopentene and tar. In both cases, traces of water serve as hydrogen bond donor and acceptor to facilitate proton transfer and make the reaction possible. One of the consequences of so many competing mechanisms is some very interesting trends we can observe. For example, both electron withdrawing groups and electron donating groups on a benzene ring makes decarboxylation easier, but the unsubstituted benzoic acid is the hardest. Isn't this absurd at first glance? But as we dig deeper, we see that the underlying mechanism is different, and the concerted proton transfer route is naturally easier than the anionic mechanism. What's more, carboxylic acids with additional electron withdrawing groups like trinitrobenzoic acid decompose very easily, as the carbanion intermediate becomes more stable. But extra electron donating groups doesn't make the reaction easier, since more proton transfer does not affect reaction rate that much. You see, with the help of understanding reaction mechanisms, we can get so many insights just from analyzing the data from a few molecules. Chapter 8. Special Reaction Mechanisms. This chapter includes mechanisms that doesn't appear in organic chemistry lectures, but find extensive use on industry and beyond. The catalytic mechanism of enzymes is introduced superficially during chapter 6, but I won't dig deep into it here because it is simply impossible. The enzymes we looked at are only one category of enzymes called paradoxo-dependent enzymes, and other enzymes like oxalate decarboxylase and pyruvate dehydrogenase have completely different mechanisms, many of which humanity cannot explain or even understand in great detail. But fortunately, paradoxo-dependent enzymes are intensively studied, and their mechanisms is generally elucidated, involving the formation of a sheaf base and a conjugate stabilized decarboxylation step. Metal catalysis is another prosperously growing field of decarboxylation, and its mechanism is generally divided into homogeneous and heterogeneous categories. The homogeneous mechanism almost exclusively features transition metal complexes and the formation of carbon-metal bonds. Some examples of transition metals used are palladium, copper, and silver, and common ligands include phosphines and phenolphthaleins. On the other hand, heterogeneous metal-catalyzed decarboxylation reactions don't have a simple mechanism, and the reaction is believed to occur through adsorption and desorption on catalyst surfaces. The compounds of nearly all metals and even some nonmetals can be used, and each offer slightly different efficiency, cost, and selectivity. You can visually see how many metals can be used here. This periodic table includes the portion of elements whose compounds are reported as catalysts in at least one academic journal, and honestly, the rest of the elements aren't there simply because they're too expensive and uneconomical to use, not because they don't actually have catalytic activity. I don't think any other single reaction can encompass so much different catalysts. Decarboxylation is just so versatile. Chapter 9. Problems. Despite shocking advantages, there are also serious setbacks that prevent decarboxylation from being widely used, at least for now. The most pronounced problem is complicated side reactions caused by the high heat required. Since the carbon-carbon bond is quite hard to break, high temperature is almost always necessary to facilitate decarboxylation. In turn, the temperature may promote amide condensation and esterification, such as the formation of phenylsalicylate and salicylic acid polymers during the decarboxylation of salicylic acid. Even worse, high temperature might induce rearrangements that completely alter the core structure of the molecule, and of course, high heat would inevitably generate tons of tar, which a YouTube guy dubbed the world's greatest tar creator has fortunately displayed to us numerous times. Alright, that's a not so funny joke, but you get what I mean. There is another fundamental reason that makes decarboxylation less commonly encountered in organic synthesis. It is essentially removing an active functional group from an otherwise inert carbon backbone, and that is usually undesirable in designing a synthetic route aimed for the interconversion of functional groups. However, decarboxylation is still very useful to remove the carboxyl functional group during late stages of the synthesis so that it doesn't appear in the product, like from cubane dicarboxylic acid to cubane itself. Chapter 10. The reverse, carboxylation. After finishing our main discussions about decarboxylation, this final chapter serves as an extra supplement about its reverse reaction, carboxylation. The most prominent carboxylation reaction is the Kolbe-Schmidt reaction, where phenols and carbon dioxide react under alkaline conditions to afford aromatic hydroxy acids. It is used industrially to synthesize salicylic acid from phenol, which is exactly the reverse of the phenol preparation we have covered earlier. Apart from industrial uses, lab conditions that eliminate the high pressure requirement are also being developed rapidly, and certain activated phenols like resorcinol can even react at ambient pressures in aqueous solution. The final topic of this video is an enzyme known as ribulose biphosphate carboxylase oxygenase, or Rubisco for short. Just as its long name suggests, it catalyzes the reaction between ribulose biphosphate and carbon dioxide or oxygen. Since this is an essential reaction in photosynthesis, Rubisco exists in all plants, making it the most abundant and arguably the most important enzyme on Earth. After all, nearly all species on the planet rely on this enzyme to obtain energy and survive, of course, including us humans. A very interesting feature of Rubisco is that it can use both carbon dioxide and oxygen as substrates depending on specific cell conditions, and only the reaction with carbon dioxide is the intended reaction to fix atmospheric carbon. Hence, plants must do their best to promote the enzyme to use carbon dioxide instead of oxygen. The reaction mechanism of rubisco is heavily investigated but still not absolutely certain, and generally believed to occur through a nucleophilic attack by the enol form of RUBP on carbon dioxide. And with this, the knowledge-intensive and hopefully fascinating journey calls to an end, and I want to say thank you for those who followed with me until here. I think that ending the video with rubisco really fits the theme, as it calls back on how decarboxylation always accompanied humanity and even all living things, despite how we gradually forgot it over centuries and then picked it up at the verge of the new millennium. See you soon.